Where have all the cowboys gone today? Okay, we're looking at another Gauss's law example, but this time we're changing it up so that we're going to look at a plane of charge. So this is actually an infinite plane of charge. Well, it's a bad infinite symbol. Let's make that a little better. There we go. So we've got an infinite plane of charge here. So it stretches off in all directions, and it has some positive charge distribution on it. It's kind of hard to say, like, you know, what's your infinite plane of charge, but it's got a charge distribution on it, okay? What we want to do is we want to find, at a point in space, what's the E field? We're seeing a lot of this with Gauss's law. So how would we go about doing this? Well, we need to make some sort of Gaussian surface in order to set up this integral. Remember, the Gauss's law integral states that a closed surface integral of the electric field dotted through the area vector is going to equal the charge enclosed inside of that surface divided by epsilon naught. And this technically is what we call the electric flux. So how do we draw a shape in order to catch the E field here? Because the E field coming off of this plane is, you know, acting directly upward. So how do we get this E field? Well, what we're going to do is we're going to use a cylinder again, but we're not going to use it like we did with the wire example. We're going to use it in a slightly different way. We're going to do this. Let's draw our cylinder going down into the plane like this. Then it comes out the other side here like that. This is our cylinder. And if we think about this, because the electric field is coming up, it's passing through the cylinder in the same direction as that normal vector. So since the E field's passing in the same direction as the normal vector, this is very nice because now our dot product essentially means nothing here. That cosine term's just going to be 1, and it goes away. What we also see that's nice is that the sides of this cylinder don't do anything. Okay, so when we want the total flux out of this, all we need to care about is the surface area of the top of the cylinder, with one little catch. The way I've drawn this here, it looks like the E field's only going up. That's not exactly true. The E field's also going down, which means that it's going down through the bottom of the cylinder. And remember, there's another area down here. So we're going to catch the flux going through the top and the bottom of the cylinder. It'll be the same amount, but it's going to be twice as much. So what we can say then is that if we go over here and we take a look at this integral, we can say that our closed path integral of an area is just going to be the area of a circle, which we well know is pi r squared. So we're going to have E multiplied by pi r squared, where r is just, you know, what's your radius vector here. And since it's the top and the bottom, we need to do this twice, okay? So this represents the top and the bottom. Sometimes students actually just write this as 2 pi r, but remember 2 pi r is a circumference. It's like the length of your circle. This is really just pi r squared in area times 2 for the top and the bottom. And that's going to equal some charge enclosed divided by epsilon naught. Now, the amount of charge that we've enclosed inside of this is given to us by some amount of a surface density here. So what we can say is that our charge we've enclosed in this is equal to a surface charge density multiplied by some area. And in this case, this is actually really nice here because if we go ahead and let's just put this value in for Q enclosed. If we do this, we're going to have E times 2 pi r squared equals sigma A over epsilon naught. Now, why does this matter? That kind of looks weird. What is pi r squared? Pi r squared is an area. Whooshing, whooshing. Areas go away. It actually doesn't matter the shape we choose for this. Circles just make nice shapes so we can show that it's just a pi r squared. But in the end, whatever that area is we pick, it doesn't matter. Pick a weird hexagon. Doesn't matter. The areas go away off of this here, which means that our electric field for an infinite plane is just going to equal the charge density divided by 2 epsilon naught. And you know what? We've, in a way, already seen this. Whenever we went back and we did the E field for a continuous disk, this right here, this sigma over 2 epsilon naught, that's what we were able to say whenever the radial vector of our disk was infinite. When our disk was infinite, we had that the E field of that disk was just the density over 2 epsilon naught, and this other term kind of went away. We see the same thing once again here for this infinite disk. We get back the exact same answer, which is a really cool thing about that there. Note, if you wanted to, you could kind of write this in a slightly different way. Some people don't write sigma here, they write the zeta instead. That's fine. Some people like to recognize that 2 epsilon naught in the denominator starts to look like something else, and what they'll do is they'll multiply it by 2 over 2 and pi over pi. The reason why is when you do that, you're essentially multiplying by 1, but what you'll get instead is you'll get a 2 pi and then the charge density divided by 4 pi epsilon naught, and some people just like to write this as 2 pi k sigma. So all of these are the exact same, however you like to write it, but some people really like to use Coulomb's constant. Personally, I just like this out here. I think this looks nice and great for that answer. But that's how you can do this for an infinite charged plate that exists. The big thing here is, you're still grabbing charges again, but make sure you're including the top and the bottom of the plate. You've got an extra 2 that bounces out here, okay? And your shape doesn't matter. All you need is some amount of area. It is possible to take this same idea here and, if we're doing this for an E field, there's nothing saying that we can't do all of what we've been doing with Gauss's law for a gravitational field, right? Because we're going to have some flux of that gravitational field moving through things. So this would kind of be a neat exercise if you wanted to go through and do all of this with gravity to see how this would kind of play out in a similar way, how it could play out in a slightly different way. It's kind of a neat thing there. If you had an infinite plate like this is actually something known as a Bowger plate, which takes place slightly, just briefly, in Arthur C. Clarke's book, 2010 Odyssey 2, which is a kind of a neat little play on the Bowger plate and this kind of mathematics, but using gravity instead. So just a little factoid trivia for you. Okay, but this is also what's going on here. Pretty straightforward Gauss's law, and that takes us through the 3 main ways to use Gauss's law: spheres, cylinders for wires, and the top and bottom cylinders, or just some area for plates of charges. At this point, it's just a matter of getting more practice with Gauss's law, just running through more practice problems, more free response questions. The College Board likes to mix it up in years. They like to give you insulators, they like to give you conductors, they like to give you things where densities are like a function of radius, where there's some constant and then 1 minus r over r. They like doing stuff like this, make it a little bit more challenging. So definitely check out the videos I have created for the AP Physics C, E&M free response questions and go through some of these Gauss's law problems. You know how to do the basic derivations of them, you know what to think there, but the real change up is, how much charge am I going to be containing in some region here, and I might have a weird density or something non-uniform that I might have to do that over, okay? But for right now, this video is finished. Adios, best of luck, and y'all take it easy.